For 30 years, astronomers across Europe pointed their telescopes at the sun and found almost nothing, no spots, no blemishes on that blinding gold disk. Why would the most dependable object in the sky simply stop behaving as it always had? And could it happen again, this time, with 8 billion of us wired into a civilization that a quiet sun could unravel? I've spent the better part of a month with sunspot ledgers, tree ring carbon isotopes, and helioseismology data, and I can tell you the answer is not what you'd expect. This is the story of the sun's silence. Every second, without pause, without hesitation, without a single instant of rest in over 4.5 billion years, our sun converts roughly 600 million tons of hydrogen into helium in its core, a furnace so relentless that even a tiny fraction of that reaction, about 4 million tons of mass converted directly into pure energy every second, in accordance with Einstein's mass-energy equivalence, is enough to keep every ocean on Earth liquid, every leaf photosynthesizing, and every one of us alive. It is, by any reasonable measure, the most reliable machine in our neighbourhood of the galaxy. And yet the sun is not in fact constant. It breathes, it has moods, and every 11 years or so, its magnetic field flips entirely, north becoming south and south becoming north, in a slow-motion reversal that we still do not fully understand. That breathing has a name, the solar cycle. It was discovered almost by accident, and the story of how we found it says something about how science actually works, which is to say, messily, stubbornly, and often by people the establishment did not take seriously at first. The man who found it was not a professional astronomer. Heinrich Schwabe was a German pharmacist who had inherited his family's apothecary business in Dessau, and who used his modest income to indulge an obsession. He wanted to be the one to discover a hypothetical planet inside the orbit of Mercury, a phantom world some 19th century astronomers called Vulcan. The theory was that such a planet, if it existed, would occasionally cross the face of the sun as a small dark dot, a transit visible only to someone patient enough to watch and watch and watch again. Schwab never found his planet. It didn't exist. But between 1826 and 1843, 17 years of near-daily observation, weather and eyesight permitting, he recorded every dark spot he saw on the sun's surface instead, cataloguing thousands of individual sunspots with a diligence that borders on the devotional. And what he noticed, buried in that mountain of data, was a rhythm. The number of spots rose, peaked, fell to almost nothing, and then rose again, on a cycle of roughly 11 years. He announced it in 1843. Almost nobody paid attention. It took another Swiss astronomer, Rudolf Wolf, to rescue Schwabe's discovery from obscurity. Wolf combed back through historical records, old observatory logs, private journals, second-hand accounts stretching back to the invention of the telescope itself, and in 1852 he formally designated the cycle we now call Solar Cycle 1 as having begun in February of 1755. We are, as I write this, deep into Solar Cycle 25. 270 years of continuous numbering, an unbroken thread connecting Schwabe's pharmacy in Dessau to the space weather satellites orbiting above us right now. Here is the part that should stop you for a second. Sunspots are not blemishes, not scars, not anything structural at all. They are magnetic phenomena, regions where twisted, concentrated bundles of the sun's magnetic field punch up through the surface, and in doing so, suppress the convection that normally carries heat from the interior outward. A sunspot is, counterintuitively, cooler than the surrounding surface, around 3,500 degrees Celsius rather than the usual 5,500, which is precisely why it looks dark against the blazing photosphere around it. It isn't a wound, it's a magnetic knot, and the number of these knots, waxing and waning across 11 years, turned out to be our best visible proxy for something we cannot see directly at all: the strength of the vast, churning magnetic engine buried deep inside our star. That engine is called the solar dynamo, and it is the thing this entire story revolves around. Because if the dynamo is what generates sunspots, and the dynamo can strengthen and weaken on a predictable 11-year rhythm, then a question naturally follows, one that took astronomers over a century to even properly ask. What happens if the dynamo doesn't just weaken on schedule but stumbles? What happens if, instead of the usual quiet trough between cycles, the sun simply stays quiet? Not for a year, not for two, but for decades. That is not a hypothetical. It happened. We have the records. And what those records reveal is stranger and more consequential than most people realise. In 1893, a British astronomer named Edward Walter Maunder, working at the Royal Observatory in Greenwich, revisited a puzzle that had first been raised by another astronomer, Gustav Spörer, a few years earlier. Both men had noticed something odd buried in the historical sunspot record. The same record that Rudolf Wolf had painstakingly reconstructed decades before. Between roughly 1645 and 1715, a stretch of 70 years spanning the reign of Louis XIV of France, sunspots had all but vanished from the observational record. Not fewer sunspots, not a weak cycle, almost none at all. Astronomers of the period, capable observers, using some of the best telescopes then available, men who had every reason and every instrument needed to see sunspots if they were there, recorded perhaps 50 spots across 3 full decades. Compare that to a typical modern solar cycle, which produces somewhere between 40,000 and 50,000. Maunder published his findings. And then, for the better part of the 20th century, almost nobody believed him. This is worth sitting with, because it tells you something about how science can go wrong, even when it's being careful. The prevailing assumption among solar physicists for most of the 1900s was that the 11-year cycle was a fixed, near immutable property of the Sun, as reliable as a heartbeat, and that any apparent gap in the historical record was simply a failure of observation rather than a failure of the Sun to produce spots. Telescopes were primitive, records were lost. Astronomers, the thinking went, just weren't looking carefully enough, or weren't publishing what they saw. The idea that the Sun's magnetic engine could simply throttle down for 70 consecutive years and then throttle back up again as if nothing had happened seemed too strange, too unprecedented, and frankly too inconvenient for a model of stellar behaviour that astronomers had built their careers on. But here is the detail that should give you pause. This quiet period, this 70-year gap, now known as the Maunder Minimum, sits almost perfectly inside a stretch of European and North American history, remembered for brutal, anomalous cold. Frost fairs were held on the frozen River Thames. Glaciers in the Alps advanced into farmland that had been cultivated for generations. Baltic sea pack ice, in some winters, reportedly grew thick enough to support sledges travelling between Sweden and Denmark. Crop failures triggered famine and unrest across parts of Europe. Historians call this broader era the Little Ice Age, and it stretched well beyond the 70 years of the Maunder Minimum itself. But the coincidence in timing was too precise, too visually dramatic, to ignore. A quiet sun, a cold earth, cause or coincidence? That question, the one Maunder himself never fully resolved, sat dormant in the scientific literature for most of a century, mentioned in footnotes, occasionally debated, largely forgotten. It would take an outsider, decades later, willing to be laughed at, to drag it back into the light. I'll get to him. His story, to my mind, is one of the more overlooked hero scientist narratives of 20th century astronomy, and it deserves more attention than it usually receives. But first, we need to sit inside the mystery itself, because there are at least 3 questions the Maunder Minimum raises that we still have not fully answered, questions that will keep resurfacing throughout everything that follows. First, was the historical sunspot gap real, or was it simply an artifact of poor record-keeping in the 1600s? Second, if it was real, what inside the Sun could cause its magnetic dynamo to essentially idle for 7 straight decades and then recover? And third, the one that should concern you most directly, if the Sun did it once, 350 years ago, is there any reason to believe it couldn't do it again, quietly right now, in the early stretch of the 21st century? I find that third question genuinely unsettling, and I don't think that's an overreaction. We have built a civilization almost entirely dependent on electromagnetic infrastructure, satellites, power grids, GPS constellations, undersea data cables carrying the entire financial system, and every piece of that infrastructure exists in a delicate, largely unspoken negotiation with the behaviour of our star, a star we have been seriously measuring for less than 300 years, which is to say, less than one full recorded grand minimum and one recovery ago. So let's ask the obvious next question. How do we even know the Maunder Minimum was real, and not just a case of 17th century astronomers looking the other way? The trouble with relying on historical sunspot observations alone is that they depend entirely on human diligence, human instruments, and human record-keeping surviving the centuries intact, and all three of those things are notoriously unreliable. A war destroys an observatory's archives. A telescope is poorly made and simply cannot resolve small spots. An astronomer gets bored or ill or dies, and nobody continues the log. If the only evidence for a 70-year solar silence is a set of increasingly sparse paper records from the 1600s, skeptics have every right to ask whether we're looking at a real astronomical event or a gap in human attention. This is where the story takes a turn that I find, honestly, one of the more elegant pieces of detective work in the whole history of solar science. Because it turns out the sun leaves fingerprints that have nothing to do with telescopes at all. Fingerprints buried in the air itself, and from there, in trees, in ice cores, in the growth rings of wood that predate the invention of the telescope by thousands of years. Here's the mechanism. High above our atmosphere, the galaxy constantly rains down cosmic rays, high-energy particles flung across space by exploding stars and other violent events far beyond our solar system. When these particles slam into nitrogen atoms in Earth's upper atmosphere, they occasionally trigger a nuclear reaction that produces a radioactive isotope of carbon, carbon-14, the same isotope famously used in archaeological dating. A similar cascade of cosmic ray collisions also produces beryllium-10, an isotope that eventually settles out of the atmosphere and gets locked into ice sheets, layer by layer, year by year, like a diary written in frozen precipitation. Now here's the part that connects all of this back to the Sun. Our star's magnetic field doesn't just sit there, it extends outward into space, inflating a vast magnetic bubble called the heliosphere that envelops the entire solar system, Earth included. When the Sun's magnetic activity is strong, many sunspots, a vigorous, well-fed dynamo, that bubble is correspondingly strong, and it does an efficient job of deflecting incoming galactic cosmic rays away from Earth. But when the Sun goes quiet, that shielding weakens, more cosmic rays get through, and more carbon-14 and beryllium-10 get produced in our atmosphere. In other words, a quiet Sun leaves behind more of these isotopes. A loud, active Sun leaves behind fewer. It's an inverse relationship, but it's an astonishingly precise one, and it means that every tree ring, every ice core layer is quietly recording the state of the Sun's magnetic field for every single year it existed, whether or not anyone was watching through a telescope at the time. When researchers eventually cross-referenced the historical sunspot gap of 1645 to 1715 against carbon-14 concentrations preserved in tree rings from that exact period, the isotope levels spiked precisely where they should have if the Sun really had gone quiet, not roughly, not approximately. The isotope record and the historical sunspot record lined up. The Maunder Minimum was not a failure of 17th century record keeping, it happened. And once scientists had this isotope technique in hand, they didn't stop at 1645. They kept going backward through the tree rings and the ice cores, reconstructing solar activity across 9,000 years of Earth's history. 9 millennia during which no human being ever pointed a telescope at the Sun because telescopes wouldn't be invented until 1608. What they found reframed the entire question. The Maunder Minimum was not a one-off anomaly, a freak 70-year glitch in an otherwise perfectly regular star, which was one entry in a long recurring pattern. Researchers identified similar grand minima at other points across the last 1,000 years alone. The Spera Minimum stretching from roughly 1450 to 1550, the Wolf Minimum around 1280 to 1350, the Oort Minimum centred near the year 1010 to 1050, and more recently and more troublingly, the Dalton Minimum from about 1790 to 1830, close enough to our own era that we have reasonably detailed instrumental records of it happening. This is, to my mind, one of the more consequential reframings in the whole history of solar physics, and it deserves to be better known outside specialist circles. The Sun does not have one fixed personality. It has at least two: a normal mode, cycling reliably every 11 years between quiet and active, and a grand minimum mode, in which that cycle persists in form but collapses in amplitude, sometimes for decades at a stretch. And across 9,000 years of isotope-reconstructed history, researchers have now catalogued more than 24 such grand minima. The Sun going quiet, it turns out, is not the exception. It is closer to a recurring feature of how our star behaves, one we happen to only rediscover in the last 150 years, because we'd forgotten to keep records long enough to notice the pattern the first time around. Which raises the paradox at the heart of everything that follows. If grand minima recur roughly once every couple of centuries, on average, and if the last one, the Dalton Minimum, ended around 1830, then simple arithmetic should make you sit up a little straighter. We are right now roughly 2 centuries removed from the last time the Sun's dynamo faltered for an extended stretch. Solar physicists have a term for the uneasy question this raises. Some have started calling it the grand minimum problem. We know these events happen. We know roughly how often, and we have almost no reliable way of predicting exactly when the next one will begin, or how severe it will be when it does. To understand why we're so bad at predicting the Sun's silences, you have to understand what's actually producing its noise in the first place. And this is where the story gets genuinely difficult, because the honest answer is that nobody has ever directly observed the machinery responsible. Not once. Not with any instrument we currently possess. The Sun is not a solid, uniformly rotating ball the way Earth is. It is a sphere of plasma, ionized gas so hot that atoms are stripped of their electrons, and because it has no solid surface to enforce uniform rotation, different parts of it spin at different speeds. The equator completes a rotation in about 25 days. The poles take closer to 35. This mismatch is called differential rotation, and it is the essential ingredient of the process solar physicists call the Babcock model, first proposed by Horace Babcock in 1961 and refined considerably since. Here's roughly how it works. Deep inside the Sun, at the boundary between the radiative interior and the outer convective zone, a churning region called the tachocline. Differential rotation takes what starts as a relatively simple, orderly magnetic field and stretches it, twists it, and winds it into increasingly tight, tangled ropes, the way pulling on opposite ends of a loosely coiled garden hose will eventually snarl it into knots. Those knots of concentrated magnetic field, buoyant relative to the surrounding plasma, rise toward the surface. Where they punch through, we see sunspots. As the cycle progresses across roughly 11 years, the tangling reaches a kind of critical, chaotic peak, solar maximum, after which the field reorganizes, flips its global polarity entirely, and begins winding up again in the opposite direction. 2 full 11-year cycles, one of each polarity, make up what's sometimes called the complete 22-year magnetic cycle of the Sun. That's the theory, and it does a genuinely good job of explaining the 11-year rhythm most of the time. But it says almost nothing, on its own, about why the whole engine might occasionally stall for 70 years and then restart. And here is where I have to be honest with you about the limits of current science, because I think documentaries too often paper over this kind of uncertainty in favour of tidy resolution, and the tidy resolution simply doesn't exist yet. We cannot see the tachocline directly. It sits roughly 0 kilometres below the visible surface, far too deep for any telescope, however powerful, to image. What we have instead is a technique called helioseismology, essentially listening to the Sun, the way geologists listen to Earth through seismic waves, except the waves rippling across the solar surface are sound waves generated by the boiling turbulence of the convective zone itself. refracted and reflected by the varying density and temperature of the layers beneath. By analysing how these acoustic waves oscillate across the visible disk, solar physicists can infer, indirectly, the structure and flow patterns of the Sun's hidden interior. The way a doctor might infer the shape of an unseen organ from an ultrasound, heliosismology has revealed something called torsional oscillations, slow, banded patterns of faster and slower rotation that migrate across the Sun's surface in sync with the solar cycle, evidence that whatever engine is driving sunspot production leaves a detectable signature even when we can't watch the engine itself. Recent analysis, some of it published only within the last couple of years, has pushed to identify precisely how deep these oscillations extend, whether the dynamo's true engine room sits in that narrow tachocline boundary, or whether it might actually originate nearer the surface, in the outer 10% or so of the Sun's radius, a possibility that would require rewriting a fair portion of the standard dynamo model. This is not a settled question. Solar physicists are, as I write this, actively disagreeing with each other about where inside our own star the sunspot cycle is actually manufactured. Let that sink in for a moment. We have spacecraft that have flown through the Sun's outer atmosphere, and we still cannot agree on where, inside the star closest to us in the entire universe, its defining rhythm is generated. There is a genuine theoretical case, though, for why the dynamo might occasionally weaken into a grand minimum. Some models suggest that the process is inherently a little chaotic, not perfectly periodic, but closer to what mathematicians call a nonlinear oscillator, one whose amplitude can wander unpredictably even while its underlying period stays roughly fixed, the way a poorly tuned engine might still turn over reliably every few seconds while occasionally sputtering and nearly stalling before catching again. Other models point to random fluctuations in the meridional flow, a slow, large-scale circulation of plasma that carries magnetic flux from the Sun's equator toward its poles and back down again, a kind of solar conveyor belt, suggesting that if this flow happens to slow down or destabilize for an extended stretch, the whole magnetic amplification process downstream could falter with it. Neither model, as of today, allows solar physicists to predict a grand minimum's onset with any confidence beyond roughly a solar cycle or two in advance. We are, in a very real sense, watching the smoke without being able to see the fire, while the internal machinery of the dynamo remains genuinely disputed among specialists. The external evidence for grand minima recurring is not disputed at all. It's sitting in ice cores on every continent, waiting to be read, and it was one man, working largely alone, dismissed for years as an outsider dabbling in a field that wasn't his own, who forced the scientific establishment to take the Maunder Minimum seriously again after nearly a century of neglect. His story is the emotional centre of everything I've told you so far, and I think it deserves the space to be told properly. His name was John Allen Eddy, though almost everyone who knew him called him Jack, and by the early 1970s, his career should have been, by conventional academic standards, somewhat stalled. He was a solar astrophysicist working at the High Altitude Observatory in Boulder, Colorado, a serious researcher with a genuine background in solar physics. He had studied eclipse observations and coronal structure and had even served, in an administrative capacity, with NASA during the Skylab era. But by his own later account, he had become restless with the narrow technical questions that dominated mainstream solar research in that decade, and he had begun spending his spare time on something most of his colleagues considered, at best, a curiosity, and at worst, a waste of a competent scientist's talent: the dusty, largely forgotten historical record of naked eye and early telescopic sunspot observations stretching back through European and even ancient Chinese and Korean astronomical archives. I find something genuinely moving about this part of the story, and it's worth pausing on. Eddy was not, at the time, working on a grant specifically targeting the Maunder Minimum. He was, in the words of one historian who later studied his career, closer to a dilettante wandering outside his own subfield. a solar physicist reading century-old astronomical journals and Jesuit missionary reports from Imperial China, cross-referencing them against tree-ring carbon-14 data that had only recently become precise enough to be genuinely useful. This was not glamorous work. It was months of comparing faded observational logs, checking translation accuracy on centuries-old Chinese court astronomer records of guest stars and solar blemishes, and building, essentially by hand, a dataset nobody else had bothered to assemble in quite that combination before. What he found, cross-checked against the newly available isotope data, confirmed something far more dramatic than a simple gap in 17th century record-keeping. Not only had the Maunder Minimum been real, the Sun genuinely had produced almost no sunspots for roughly 70 years, but the aurora borealis, normally visible at high latitudes whenever the Sun's activity stirs up Earth's magnetic field, had also all but vanished from the historical record during precisely that same window. European chroniclers, who wrote in detail about comets, eclipses and other celestial events during those decades, simply stopped mentioning the northern lights almost entirely, a silence that would have been almost impossible if the Sun's magnetic activity had continued at its normal 11-year rhythm underneath the surface. Eddy published his findings in June 1976, in a paper in the journal Science titled simply The Maunder Minimum. It is not an exaggeration to say that this single paper revived interest in a phenomenon that had been sitting, largely unread, in the footnotes of solar physics for 80 years. It has since been cited more than 3,000 times, a staggering figure for a paper built substantially on historical archive work, rather than new instrumental data. Eddy did not discover the Maunder Minimum. Spörer and Maunder himself had done that in the 1890s. What Eddy did was something arguably harder. He resurrected a dead idea, armed it with independent physical evidence from tree rings that the original discoverers never had access to, and forced an entire scientific generation that had convinced itself the sunspot cycle was essentially immutable to accept that their own star had, within recorded human history, simply stopped behaving the way their models said it should. I will admit, when I first read through the details of Eddy's reconstruction, the sheer, patient cross-referencing of Chinese court astronomer logs against European telescopic records against Greenland ice cores, I had to put the material down for a moment and just sit with it. There's something about a lone researcher, working largely outside the mainstream current of his own field, piecing together a truth that overturns a consensus, that feels almost mythic. But it wasn't myth. It was archival grind, patience, and a willingness to trust old, unglamorous records that everyone else had decided weren't worth the trouble. And here's the detail that gives Eddy's story its real weight, the one that connects his solitary archival obsession directly back to the stakes we're building toward. Once Eddy had established that the Little Ice Age and the Maunder Minimum overlapped so precisely, he didn't stop at historical curiosity. He began asking, publicly in interviews and later papers, whether a modern grand minimum could happen again, and if it did, what it would mean for a civilization now utterly dependent on technologies that hadn't existed the last time the sun went quiet. Telegraph wires hadn't existed in 1645. Power grids hadn't existed. Satellites, GPS constellations, the entire electromagnetic nervous system of modern life. None of it existed the last time our star took a 70-year breath. Eddy, in the 1970s, was one of the first serious scientists to ask on the record, what would happen if it happened now, to us, instead of to them? He died in 2009, having lived to see solar physics fully absorb the reality he'd spent years re-establishing. But the question he raised in the 1970s, not whether the sun could go quiet, because by then that was settled, but what would happen if it did so again, inside a civilization wired the way ours is, remains, even now, disturbingly open. And it's the question I want to spend the rest of this story pressing on, because the honest answer is considerably more complicated and considerably higher stakes than most casual treatments of this topic let on. Here is where the stakes need to climb, because up to this point I've been describing a mystery largely confined to the past. Old ledgers, old ice cores, an old astronomer's archival grind. But the Sun's activity doesn't only matter in the slow, decades-long sense of grand minima and little ice ages. It matters violently, on timescales of minutes and hours, and the evidence for that lives in one of the more genuinely alarming episodes in the history of applied astronomy. On the 1st of September 1859, a British amateur astronomer named Richard Carrington was doing something he did most clear mornings, sketching sunspots at his private observatory in Redhill, south of London, projecting the sun's image through a telescope onto a screen so he could trace the shapes of the spots by hand without damaging his eyes. That particular morning, he was watching an unusually large and complex sunspot group when he saw something no one had ever documented before: two brilliant points of white light suddenly flaring within the sunspot group itself, intensifying over about 5 minutes before fading. Carrington had just become the first person in recorded history to witness a solar flare, and, with a mixture of excitement and disbelief that I find entirely relatable, he later wrote that he hastened to the succeeding room to call someone to witness the exhibition before it ended, only to find it already fading by the time he returned. Nobody believed the flare itself would matter much on Earth. He was wrong. Roughly 17.5 hours later, remarkably fast, given that a coronal mass ejection typically takes 1 to 3 days to cross the 93 million miles between the Sun and Earth. A wall of charged particles slammed into our planet's magnetic field, triggering the most intense geomagnetic storm ever recorded in human history. Auroras, normally confined to high latitudes near the poles, were reported as far south as Hawaii, the Caribbean and Colombia, close enough to the equator that some observers reportedly could read newspapers by their light at midnight. Telegraph systems across Europe and North America, the most advanced long-distance communication technology that existed at the time, went haywire. Operators reported sparks leaping from their equipment. Some lines continued transmitting messages for hours even after operators disconnected their batteries entirely. Powered instead by the induced current the storm itself was generating in the wires. It became known as the Carrington event, and for over a century it remained largely a historical curiosity, a dramatic but survivable anecdote from an era when the most advanced electrical infrastructure on Earth amounted to a few thousand miles of telegraph cable. We do not have that luxury of scale anymore, and we got a considerably smaller but far more costly preview of what a modern equivalent might look like on the 13th of March 1989. A geomagnetic storm, nowhere near Carrington scale, but powerful enough, struck Earth's magnetosphere and induced currents in the long transmission lines of Hydro-Quebec's power grid in eastern Canada. Those induced currents overloaded transformers and tripped protective relays in a cascading failure that took down the entire provincial grid in about 90 seconds, plunging roughly 6 million people into darkness in the dead of a Canadian winter night, some of them for as long as 9 hours. Transformers as far away as New Jersey were damaged. This was not a hypothetical scenario modelled by a worried physicist. It happened within living memory to a fully modern electrical grid, and the storm responsible for it was a fraction of the intensity of the one Carrington witnessed in 1859. Now here's the connection back to everything we've established about grand minima, and it's a genuinely important nuance that a lot of casual coverage of this topic gets backward. A quiet sun, a Maunder Minimum style grand minimum, does not necessarily mean a safer sun. In fact, in one specific and counterintuitive sense, it can mean the opposite. When the sun's overall magnetic activity weakens, the heliosphere, that vast magnetic bubble I described earlier, the one that shields the solar system from galactic cosmic rays, weakens along with it. Less shielding means more cosmic rays reaching Earth's atmosphere, which means more radiation exposure at high altitudes for astronauts and airline crews on polar routes, more disruption to sensitive electronics, and, according to reconstructions using the same beryllium-10 and carbon-14 techniques Eddie relied on, measurably elevated radiation environments throughout the historical grand minima we've already discussed. A quiet sun trades one kind of risk for another, fewer flares and fewer coronal mass ejections in the short term, generally speaking, but a persistently leakier shield against a background hazard that never stops raining down from deep space. This is the paradox worth naming clearly, because it upends the intuitive assumption that a silent sun is simply a calmer, gentler one. Solar physicists have started referring to this trade-off, somewhat informally, as the quiet sun paradox. The very same magnetic quietude that suppresses violent solar storms is also the thing that lowers our shielding against a different, more diffuse, and in some ways more insidious form of radiation exposure. One with implications not just for astronauts on future missions to Mars, but for the increasingly sensitive electronics that our entire technological civilization now depends on at ground level. And if that's true, if a grand minimum doesn't simply mean calmer weather, but instead means a genuine reshuffling of which risks we face, some reduced and others increased, then the entire casual framing of the sun going silent as either purely dangerous or purely benign collapses. It isn't one or the other, it's a different risk profile entirely, one we have never had to navigate with a fully modern, satellite-dependent, grid-reliant civilization. Because the last time it happened in the 1600s, the most advanced piece of electrical infrastructure on the planet hadn't been invented yet. And the last time we're fairly confident it happened with instrumental confirmation. The Dalton minimum of the early 1800s, commercial electricity itself was still decades away. This brings us to the question that every serious solar physicist gets asked, in some form, at almost every public talk they give. Is it happening again right now? The honest, frustrating, scientifically responsible answer is that we genuinely do not know. And the recent history of trying to answer that question is itself a useful lesson in how difficult solar prediction actually is, even with satellites, supercomputers and helioseismology that Eddie and Maunder never had access to. In 2008 and 2009, the Sun produced what solar physicists at the time called an unusually deep and extended minimum. Sunspots were absent on 266 of the 366 days of 2008, a full 73% of the year, the quietest stretch recorded since 1913. Solar wind pressure dropped to its lowest measured levels of the space age. Cosmic ray flux at Earth spiked to record highs for the era. A number of researchers watching these numbers began openly speculating that the Sun might be sliding into a new grand minimum, a modern echo of Dalton or even Maunder, and some published forecasts projecting a modern grand solar minimum persisting for decades. Solar Cycle 25, which followed, was widely predicted by the official NASA and NOAA Solar Cycle Prediction Panel to be another weak cycle, similar to or even feebler than its predecessor. It was not. By mid-2025, Solar Cycle 25 had climbed to a peak sunspot number of roughly 115 to 125, noticeably stronger than the panel's initial forecasts, and strong enough that NASA and NOAA jointly announced the Sun had reached solar maximum with an activity level that surprised much of the forecasting community. The grand minimum some had confidently predicted after 2008 simply did not materialise on the timeline they'd projected. The Sun, once again, did something other than what the models said it should. I think this deserves to be stated plainly, because it's the kind of nuance that gets lost in more sensational coverage of this subject. As of today, mainstream solar physics does not consider us to be inside, or imminently entering, a new grand minimum. The consensus view, reflected in NASA and NOAA's own public statements, is that Solar Cycle 25 turned out to be a comparatively active cycle, not a weak one, and that whatever drove the unusually deep 2008-2009 minimum was more likely a normal, if extended, low point in the ordinary 11-year rhythm, rather than the opening act of a multi-decade grand silence. This does not mean a future grand minimum is impossible. The isotope record makes clear these events recur, on average every couple of centuries, and we are now roughly 2 centuries past the end of the Dalton minimum. But it does mean that specific, confident predictions of an imminent grand minimum, the kind that occasionally circulate in less careful corners of the internet, are running well ahead of what the actual data currently support. There is a smaller, more speculative body of published research that disagrees with this consensus, at least in part. A handful of papers over the past several years have argued, using various statistical techniques applied to solar cycle length and amplitude trends, that a new grand minimum may already be underway or imminent, with some more extreme projections suggesting a period of reduced solar output persisting for decades into the middle of this century. These papers exist in the peer-reviewed literature, and I don't want to dismiss them outright, because solar prediction is a field littered with confident forecasts that were later proven wrong in both directions. But it's worth being honest that these projections remain a minority position, disputed by other researchers working with overlapping data, and Solar Cycle 25's unexpectedly vigorous performance through 2024 and 2025 has, if anything, made the imminent grand minimum case somewhat harder to sustain in the near term rather than easier. So where does that leave us? It leaves us, I think, in a genuinely uncomfortable epistemic position, and I want to be honest about that rather than paper over it with false confidence. We know grand minima happen. We know from 9,000 years of isotope data that they recur with rough but not precise regularity. We know the last one ended around 1830. We do not know what triggers their onset with enough precision to predict the next one's arrival within even a decade, let alone a specific year. And we have just watched in real time a solar cycle that the best forecasting models available confidently predicted would be weak turn out to be one of the more active cycles in recent decades instead. If anything, Solar Cycle 25 should function as a humbling case study in how far solar prediction still has to go. There's a further complication buried inside all of this, one that connects the ancient climate correlation eddy uncovered to a much more contentious modern debate. Because if a quiet sun really did contribute meaningfully to the cooling of the Little Ice Age, and the correlation with the Maunder, Spura, and Dalton minima is suggestive, even if the underlying mechanism remains debated, then a natural and politically loaded question follows. Could a future grand minimum meaningfully offset, or even reverse, the warming trend driven by anthropogenic greenhouse gas emissions? The mainstream climate science answer, and it's one I think the evidence genuinely supports, is almost certainly not, or at least not by nearly enough to matter. The proposed physical mechanism linking solar activity to Earth's climate, beyond simple changes in the sun's total energy output, is largely built around the work of Danish physicist Henrik Svensmark, who in the 1990s proposed that increased cosmic ray flux during quiet solar periods could seed additional low-altitude cloud formation, reflecting more sunlight back into space, and producing a modest cooling effect independent of the sun's raw luminosity. It's an evocative hypothesis, and it generated real scientific interest and real experimental follow-up, including cloud chamber experiments at CERN, designed explicitly to test whether cosmic rays could nucleate cloud droplets under laboratory conditions. But the broader scientific assessment, reflected in reports from bodies like the IPCC, has consistently found the observed correlation between cosmic ray flux and cloud cover too weak and too inconsistent to explain a climatically significant effect, and multiple follow-up studies have failed to reproduce the strength of correlation Svensmark's earliest papers reported, even under the most generous published estimates for a renewed grand minimum's cooling effect, typically modelled at somewhere around a few tenths of a degree Celsius of global cooling, sustained only for the duration of the minimum itself. That impact would be dwarfed by the roughly 1.1 to 1.5 degrees Celsius of warming already measured since the pre-industrial era, warming that is overwhelmingly attributed to greenhouse gas concentrations rather than solar variability. This is, I think, a case where the poetic appeal of the story, a quiet sun cooling an overheating Earth back into balance, runs directly into the far less poetic reality of the data. The sun is not coming to rescue us from our own emissions. Even in a full grand minimum, at best it would offer a brief, partial, temporary break, not a reversal. If prediction remains this difficult, the obvious next question is whether we're at least getting better at watching. And here I think the story becomes genuinely hopeful, because the last decade has produced observational tools that Eddie, working with paper archives and tree ring samples in the 1970s, could not have imagined on Christmas Eve of 2024, a spacecraft called the Parker Solar Probe, launched by NASA in 2018 and named for the physicist Eugene Parker, who first theorized the existence of the solar wind, made its closest approach yet to the Sun, passing within roughly 1 million kilometers of the solar surface, a distance that sounds enormous until you consider that it places the spacecraft well inside the orbit of Mercury and closer to the Sun, relative to Earth's distance, than a golf ball would be if you scaled the Sun down to the size of a basketball. At that closest approach, Parker's solar probe was travelling at roughly 690,000 kilometers per hour, or about 191 kilometers every single second, fast enough to cross the continental United States in well under 15 seconds, and fast enough that the probe currently holds the record, verified by Guinness World Records, for the fastest human-made object ever built. It has since matched that closest approach distance multiple times, including its 24th and 26th close passes through 2025, each pass gathering direct, in situ measurements of the solar wind and magnetic field environment in a region of space no spacecraft had ever physically occupied before. Why does this matter for the question of grand minima? Because one of the deepest limitations in everything I've described so far, the Babcock model, the tachocline, the torsional oscillations detected through heliosismology, is that almost all of it has been inferred indirectly, reconstructed from surface observations and acoustic wave patterns rather than measured directly at the source. Parker Solar Probe cannot see inside the Sun any more than any previous spacecraft could. The interior remains, and will likely remain for the foreseeable future, fundamentally inaccessible to direct instrumentation. But by measuring the solar wind and magnetic field structure at unprecedented proximity to where they originate, the mission is giving solar physicists their most detailed picture yet of how magnetic energy is actually released and transported away from the Sun's outer layers, data that feeds directly back into refining the very dynamo models that remain, as I described earlier, genuinely unsettled even at the level of where inside the Sun the engine physically sits. There's a detail in this mission that I find quietly moving, and it connects, in a strange way, back to Jack Eddy's archival grind through Chinese court astronomer records in the 1970s. Eddy had to reconstruct the Sun's hidden behaviour by proxy, borrowing evidence from tree rings and second-hand historical chronicles, because no direct instrument existed that could tell him what the Sun's magnetic field was actually doing during the 17th century. 50 years later, we have a spacecraft close enough to the Sun that its heat shield, made of a carbon composite material engineered specifically for this mission, must withstand temperatures exceeding 370 degrees Celsius on its sun-facing side, while the instruments tucked in its shadow operate at a comparatively comfortable room temperature just centimeters away. We went from reading tree rings to touching, in the most direct sense currently possible, the outer atmosphere of the star itself. That's not a small span of scientific progress to have covered in half a century, and it's the kind of achievement that, when I really sit with it, makes me feel a genuine flicker of optimism about where solar prediction might be in another 50 years. But, and this is the forward pull I want to leave hanging here, even with all of that direct data pouring in from inside the Sun's outer atmosphere, we still cannot tell you, with confidence, when the next grand minimum will begin. Proximity to the source has not yet translated into predictive power over the deepest, most stubborn mystery in all of this. What actually starts, and what actually ends, a decades-long silence in a star's magnetic heartbeat. Everything I've described so far concerns silences measured in decades, 70 years for the Maunder Minimum, 40 for the Dalton, a human lifetime or two at most. But there is a far deeper, far more permanent silence written into the Sun's future, one that operates on a timescale so vast it makes the Maunder Minimum look like a single held breath. And I think it's worth holding both timescales in your mind at once, because the contrast between them says something important about what kind of star we actually live beside. In roughly 5 billion years, current best estimates cluster around 5 to 5. 4 billion years from now, the Sun will exhaust the hydrogen fuel in its core, the same fusion reaction converting 600 million tons of mass every second that opened this whole story. Once that core hydrogen runs out, the fusion reactions powering the Sun's stability will shift outward into a shell surrounding an inert helium core, and the Sun will begin a transformation that astronomers have observed happening to countless other stars across the galaxy, but have never watched happen to their own. It will swell dramatically into a red giant, its outer layers expanding to potentially engulf the orbit of Mercury, then Venus, and according to some models, possibly reaching as far as Earth's current orbit itself, though other calculations suggest Earth's orbit may actually expand outward as the Sun sheds mass, granting our planet a narrow, scorched reprieve rather than outright engulfment. Either way, by that point, none of it will matter to anything living here, because Earth's oceans will have boiled away long before the red giant phase even begins, driven by a steadily increasing solar luminosity that current models suggest will render the surface uninhabitable well over 1 billion years before the Sun even leaves its main sequence. Here is the thing I want you to notice about this deep future silence, because it's genuinely different in character from everything else in this story. The Maunder Minimum was a temporary flicker in an otherwise stable magnetic engine, the dynamo throttled down, and then, mysteriously but reliably, throttled back up again, exactly as it always had for millennia before. The eventual death of the Sun's hydrogen-burning phase is not that kind of silence at all. It is not a pause, it is an ending, written into the fundamental physics of stellar nucleosynthesis, as certain and as unavoidable as the second law of thermodynamics itself. There is no recovery phase, there is no return to normal sunspot cycles afterward. The star that has powered every single second of biological evolution on this planet, from the first self-replicating molecules in some ancient tidal pool to the eyes reading these words right now, will, on a schedule already written into its mass and composition since before Earth itself finished forming, run out of the fuel that makes it the star we know. I find something genuinely humbling in holding these two timescales side by side. On the one hand, a 70-year quiet spell that terrified nobody at the time it was happening, because nobody at the time even knew it was happening. European astronomers in the 1600s simply kept records, some of them noticing the scarcity of spots, most of them not particularly alarmed, because the sun still rose every morning and the wheat, mostly, still grew, even in the coldest years. And on the other hand, an inevitability 5 billion years distant, so far beyond any human timescale that it borders on the meaningless in any practical sense, and yet so certain that we can already calculate, with reasonable precision, roughly which year within a margin of a few hundred million our own sun will begin to swell. Between those two extremes sits the question this entire story has been circling from the start, the one Jack Eddy first raised seriously in the 1970s, and that nobody, even now, with Parker Solar Probe's direct measurements and half a century of refined dynamo models, can answer with confidence, not whether the sun's fusion will one day end. That's settled, but whether its magnetic voice, the sunspot cycle that has rung out reliably since at least 1755, and before that, in interrupted fits and starts for millennia, might fall quiet again within our own lifetimes, or our children's, or our grandchildren's. And if it does, whether the civilization we've built, one that did not exist the last time this happened, one whose entire nervous system runs on electromagnetic infrastructure, a 17th century astronomer could not have begun to imagine, will treat that silence as a curiosity to be studied or a vulnerability to be survived. there's a particular kind of humility that comes from spending real time with a subject like this one, and it's not the humility of ignorance. We know an enormous amount about our own star, more than any generation of humans in history has ever known. It's a different kind, the humility of knowing precisely how much we still cannot predict, even with all of that accumulated knowledge sitting behind us. We know the sun has gone quiet before. We know it did so at least 5 times in the last 1,000 years alone, and dozens of times across the 9,000-year isotope record that carbon-14 and beryllium-10 have allowed us to reconstruct. We know a lone, largely self-directed astronomer named Jack Eddy spent years of his career resurrecting a forgotten discovery from dusty archives and cross-referencing it against tree rings because he trusted old, unglamorous evidence that his contemporaries had decided wasn't worth the effort. We know a modern geomagnetic storm, even one far weaker than the Carrington event of 1859, can plunge millions of people into darkness in under 2 minutes. We know, thanks to a spacecraft that can survive temperatures hot enough to vaporize most metals while flying closer to our star than any human-made object ever has, more about the outer machinery of the sun's magnetic engine than we did even a decade ago. And we know, with total certainty, that in roughly 5 billion years, none of this will matter anymore because the sun's hydrogen-burning heart will finally permanently run dry. What we do not know, what nobody currently knows, and what I don't think any documentary, mine included, is honestly entitled to resolve for you, is whether the quiet decades we've spent worrying about since Eddy's 1976 paper are already gathering somewhere in the sun's hidden interior, in a tachocline we cannot see, driven by a dynamo whose exact location inside our own star remains a live scientific argument. Solar physicists disagree right now in published papers about whether solar cycle 25's unexpected vigour rules out an imminent grand minimum, or simply delays one by a cycle or two. That disagreement is not a failure of the field. It's an honest reflection of how genuinely difficult this problem is, and I think there's something worth respecting in scientists who are willing to say, in public, in peer-reviewed venues, we don't know yet, rather than manufacturing a false confidence in either direction. I keep coming back to something almost embarrassingly simple about all of this. The sun is the single most consequential object in the story of every living thing that has ever existed on this planet, and we have been seriously, systematically watching it for less than 300 years, 3 centuries against 4.5 billion years of the sun's existence, is not even a rounding error. It is closer to a single frame extracted from a film that has been running since before this planet had continents, and within that vanishingly thin sliver of observation, we have already caught our star doing something we didn't expect, going quiet for decades, not once but repeatedly, and we still cannot tell you, with any real confidence, when it might choose to do so again. Maybe that's the most honest note to end on, not because it offers comfort, but because it offers something I think is more valuable than comfort, an accurate sense of scale. There is a strange kind of dignity in a species that has learned to read tree rings and ice cores, and acoustic vibrations rippling across a star's surface in order to reconstruct a silence that happened 3.5 centuries before any of us were born, purely because an obscure Colorado astrophysicist in the 1970s refused to believe that old, dismissed archives had nothing left to teach us. We are not the first generation to wonder whether the sun might fall quiet again. We are simply the first generation with the tools to actually watch it happen, in something close to real time, if it does, somewhere, right now, inside a layer of our star we cannot see, using a mechanism we still cannot fully name, that decision. If decision is even the right word for a process this purely physical, is already being made. We will not know the answer until the sunspots either keep coming, cycle after 11-year cycle, the way they have since 1755, or until, one ordinary year, they simply start to thin out and keep thinning, and an astronomer somewhere notices the gap and reaches, the way Jack Eddy once did, for the old records nobody else thought to check. We are the generation that learned to ask the question properly. Whether we're also the generation that lives through the answer is not something the data, however good it's gotten, can yet tell us. And perhaps that's fitting for a star that has spent 4.5 billion years reminding us, gently and then sometimes violently, that its silences were never really about us at all.